Welcome again. The last lecture of this series. In the previous lecture, we discussed the you have a internal direct product continue, and then we have to classify how to optomorphism. The internal direct product and external direct product looks like the same. We have proved that if G is an internal direct product, then it is isomorphic to the external direct product H cross K. H and K are two subgroups are there. In this class, we try to prove the fundamental theorem of finite abelian groups. So let's before proving the fundamental theorem of finite abelian groups, we have to define some p groups, and then we have to a series of results which will be help to prove the main theorem. So let's start. We will with this lecture, this the definition of a p groups. So now we have to, in this class, we try to classify finite abelian groups by decomposing an arbitrary finite groups according to the fundamental theorem of finite abelian groups. Now we have to define first is a what is a p group. Let p be a prime. A group G is a p group if every element in G has a order of p to the power k for some k. If a subgroup H of a group G is a p group, then we say that H is a p subgroup. Simply say that if we have a group is there and every element of a G is a some power of a p, then we can say that p is a prime, and for some k we can say that this is a p group, and if H is a subgroup of this GP group, then H is called as a p subgroup of a this is G. For example, I just take a Z2 and element of a Z2, you know that Z2 is equal to, you have a 0 and 1 are the elements is there, and now if you take a, because in the 2 of 1, and then you can have 1 plus under addition modulo 2, 1 is equal to 0. So this means elements of a 1 0 1 to the power 0. So element of this is 0 to the power 1 0, and 0 to the power 2 is 1 to the power 2 is again 0. So this means this is the elements of a this is called is a power of a 2, and then you have just say that 2 and 2 is 2 to the power 1 is equal to 0, 2 to the power 0 is equal to 1, and then if you take a Z4, in the Z4 you take a Z4 can be written in the form of a 0, 1, 2, 3, 4, and then you just see that this is element of a Z4 also written in the form of a this means you can just say that 1 can be written as a 4 times of a 1 is equal to 0. So this means is equal to order of this. So this means this can be written as a 2 to the 2 square, and then again is power of a 2, and then this can be 2 plus 2 is equal to 0. So 2 square, and then 2 to the, similarly you have to just all of the element of this can be representing into this form. So this means this is again is a all the element of this some powers of a 2. This means we can say that this can be representing similarly Z2 cross Z2 is also Z4 cross Z4. You know that the Z4 is element of a E, R, R square, R cube. This means, and now rotations, and then we have a reflections F, and then you have a RF, R square F, and then R to the power 3 F, and these are the elements of a this 4. Then these this means some of the elements, these are the elements of a order 2, and this is a sum of the order 2 and order 4. This means we can write in the form of a sum all the elements of a 2 to the power of a 2. That means P is a prime 2. Then we can say that is a 2 groups. So these are the examples of a clearly is a 2 group. Now again we take a 27. 27 every element of 27 can be written as some powers of a 3 because you just take a this are the element of divisor of this 3. So this is this again is a 3 group. Now we have taken 24. 24 is not a p group. Why? Because 24 8 into 3, or like this way you can just say that this is 2 to the power 3 into 3, like this form, there is some power of a 2 or 3, then a product of a power 2 and 3. For example, 12 can be written as a 2 square, some power of a 2 into 3, or this is uh, like this. So this means some power. This 18 is also written in the form of a this thing, but there is some elements of 8. 8 cannot be written as some prime power of a 2 and 3. So this means cannot be as a p group system, because we have to write as a 2 prime numbers is equal to 2 and 3. So every elements of this is the prime of a 2 and 3, but 8 is the 8 can be written as a simply is equal to, you have a 2 to the power 3, and the 3 does not involving here. So this means clearly this is not a Z24 is not a p group example. This is one of the example which is not a p group. Okay, so by Lagrange's theorem, you know that every group of order p to the power n, p is a prime, is automatically is a p group, since the order of every element must divide by p to the power n. So we will prove the converse of this for finite abelian group, because by the Lagrange theorem every this if p is a prime and group of order p to the power n, and then you have a if this p is a prime, automatically is a p group, since every the order of every elements must be divided by p to the power n. So now we will prove a converse for to this for a finite abelian group. Let G be a finite abelian group, and order of a G can be written as a in the form of a product of this primes p to the power eta 1, p to eta 2, and so on. Pi are the all are distinct primes. We take a then the set Gi is equal to G is the element of a G. Order of a G is nothing but equal to pi to the power k. K is the element of a is a subgroup of a G. So just take a some element into this, and this is nothing but is equal to is a, we try to prove that is a subgroup of this G. So as E is the order of p to the power I to the power 0, therefore E is the element of a Gi. So that means is equal to 1 is held. Now we take two elements A and B are the element of a Gi, then order of A is equal to pi to the power n is equal to identity, order of a B is equal to pi or is equal to identity. So this we can say that if this p to the power order of a G is equal to p to the I k, this means is equal to identity. So this means clearly by this order of A and order of a B we can write into this form. Let k be a larger than m and n. We take an element k is an integer larger than this m and n, and as G is abelian, then you know that A B to the power n, if G is abelian, a to the power n, b to the power n. So we take a b pi to the power pi to the power k, then a to the power pi to the power k, b to the power pi to the power k, and because this order is p to the power I is equal to n is equal to identity, and this, and then k will be larger than m and n. Whenever m is equal to identity, n is equal to identity, this is identity, then this is equal to identity, and then we can say that as order of A and order of B both are divides p to the power k, so order of AB must divide p to the power pi to the power k, and therefore if divides this means we can say that by the Gi property AB is the element of a is nothing but is equal to identity. This means we can say the A and B are the element of a Gi. Now we have to finally we take a inverse. You know that if A is the element of a Gi and order of A is nothing but is equal to order of Ai, inverse is the same by the property. What is the order of A and order of A inverse the same? So this means A inverse is also the element of a Gi. This means Gi is indeed a subgroup. This means satisfy both the property of a subgroup. So we can clearly say that this Gi is clearly is a subgroup of this group of G. So this means we can say that now note that the lemma this result we have to proving this result lemma 3.1 this does not hold for a non-abelian groups. Indeed we take one of the example S3, we can see that 1 2 and 2 3 both have the order 2, but their product is equal to this has a order 3. So this means if we have a group is a non-abelian, then this result does not hold in the case of a non-abelian. So now just we have to take a this another lemma let G be a finite abelian group of order n. If P is a prime dividing n, then G contains an element of order uh, P. So this means we can say that if we have a G is a finite abelian group of order n, and P is a prime dividing n, P is a prime and dividing n, then G contains an element of order P. So this means we have to G as a contain an element of order P. Now proof by induction. So we use the proof by strong induction. In case n is equal to 1, that is a trivial. So assume that the lemma is hold for all groups of order k, where k lies between 1 to n, and suppose P is a prime number dividing n. This is a given condition, and if G has a no proper non-trivial subgroups, then G is generated by A, and then this E is not equal to this A is the element of a G, and hence n must be a prime, and if n is a must be prime, this order of A must be is equal to P. By the property of this, we have to P is a prime dividing n, and G has a no proper, then it's not equal to identity. If it is not identity generated by this, then n must be divided by this, so n should be a prime. So this means order of A must be the prime number. Suppose G contains a non-trivial proper subgroups H, because G is abelian, then H is a normal subgroup. This is not a problem. And now we can just show that order of G can be written in the form of a nothing but is equal to, you know that by the quotient group order of H into order of G by H. And now we have a P is divide the order of H, or P is divide the order of G by H. If suppose H is equal to order of R, and R lies between 1 to n, if P divides R, then P must divide order of H. So H contains an element X of order P by inductive hypothesis, and X is the element of a G. For the other case, if P does not divide R, and so P is divides this quotient group G by H, and by the inductive hypothesis G by H contains an element of AH of order P, and then H can be written as the same as AH to the power P is equal to A to the power P into H, and now we have a H is equal to this A to the power P is the element of H. So but A does not belongs to the H, so we just said that if A, so we claim that this means if A does not belong to the H, so this means we can claim that A to the power R must be equal to this is equal to P, because A to the power P is equal to H. So E can be written as A to the power P to the power R, and this can be written as A to the power R to the power P. And now we have to just say that by this A to the power R must divides P, or A to the power order of A to the power is equal to 1, or P. If they divide this, then order of A to the power R is equal to 1 or is equal to P. Then therefore it is sufficient to show that A to the power R is not equal to identity. Then if it is not equal to identity, then it is equal to P. Since P and R are relatively prime, because of, so if these two are relatively prime, then there exists some integers R and S. This is the satisfy this condition. And now if A to the power R is equal to, you have a identity, then A can be written in the form of a to the power SP plus RT, and SP plus this A to the power P into S, R into S, and A to the power R is equal to, you have a identity. So this means this is another A P to the power S belong, and this is the again is the element of H, and this contradict that A is the element of H. A does not belongs to the H. So this means A to the power R is not equal to identity. So if A to the power R is not equal to identity, then what is the problem satisfy this? Then order of A to the power R is nothing but is equal to P. So this complete the proof of this result. We have to complete this form. Now for another result we proving which will be used into the proof of the finite abelian groups. Structure theorem: a finite abelian group is a P group if and only if its order is a power of a P. So now we say that if we have a finite abelian group is a P group if and only if its order is a power of a phi. This means we can write the power of a phi if and only if. So, if let g is equal to some order of a g is equal to power of a p to the power m, and then by the Lagrange's theorem the order of any g belongs to g must divide p to the power m, and therefore must be power of a p. Then this is a must be power of a phi, then when there is a p group is there. So, now we have to conversely if order of a g is not a power of a p, we have to prove by contradiction. If order of a g is not a power of a p, because abelian power of a p is only a p group. If it is p group, then every group of order can be written as a power of a p. Now, we have to assuming that suppose g is not a power of a p. If it is not a power of a p, there exists a prime number q which divides the order of a g by the previous lemma, and then if it q divides this order of a q, then g contains an element of order q, and this if g contains order of a q, but every element of this order is equal to p, as that means this contradict the contradiction, and if it is contradiction, that means the order of a g must be a power of a prime. So, this means this completes the again proof of this lemma. Okay, now we have to by this lemma we can immediately extend this into the form of a this form. Let G be a finite abelian P group that is not cyclic. That is important. Suppose that G belongs to G has a maximal order if X is the element of a quotient group of a G generated by G has a smallest positive order, then order of X is equal to P. Means G has a maximal order and an element X belongs to the quotient group of this G generated by G has a smallest possible order, then order of this element X is nothing but is equal to is the same as a this P. So, now we have to prove this. Let G is the element of a G be a maximal order and G. So, this means order of a G is equal to some p to the power m, some m should be less than equal to n. Since G is not cyclic, so G cannot be generated by this element of a G. Now we choose a X element in the form of a G by quotient group of this G by generated by G, where X is the smallest positive order. We can say that the order of X is equal to some p to the power L, and since E is the element of this, then X we are assuming that is not equal to E, as so L should be strictly greater than 0, but X to the power P is equal to can be written as p to the power L minus 1, and then so X to the power P is the smallest order than order of X, and hence X to the power P is the element of generated by this G by minimality of a minimality of a X. That is means we can say that is order of this X to the power is minimality by of X. This means X to the power V can be written as some G to the power S for some S, then by this G to the power S to the power because P to the power L minus 1, and this X to the power P to the power P L minus 1, and then this is nothing but is equal to X to the power P to the power L, and X to the power P to the power L nothing but is equal to you have a X to the power P to the power L is equal to identity. So, this is equal to we have to getting is the identity element. We have to then order of a GS is equal to p to the power L minus 1, which is strictly less than p to the power m. So, G to the power S is not a generator for G by this, not P must be a occur as a factor of S. This means we say that S can be written as a PR. If S can be written as a PF of R, then X to the power P is equal to G to the power S, and G to the power S is equal to G to the power P into R, and then suppose we have to define H as the form of a G to the power inverse R and X, and H is not the element of a generator of this G. So, otherwise X would have the in G, and so this means also H to the power P is equal to G of minus rp x to the power p, and now r to the power p is equal to, you have a g of inverse of s, and this is nothing but is equal to x to the power p. So you have a minus r to the power p. So this means nothing g of inverse, this is the same. So this means we can take inverse of this. So this can be giving the this is equal to g to the power minus s, and then if g to the power minus s, and this is nothing but is equal to, can be x to the power minus p, and x to the power minus p into x to the power p is equal to identity. Then we can say that h to the power p is equal to identity. If h to the power p is equal to identity, we have now formed an element h with order of p, that is h does not belongs to the generator of a g. Since x is choosing to have the smallest order for all the elements of that are not in g, hence order of x should be is equal to p. So this complete the proof of a this result. If g is be a finite abelian p group that is not cyclic, suppose this g has a maximal order. So we complete the, that means we complete the proof of this result. Let G be a finite p group that is not cyclic. Suppose G belongs to, G has the maximal order. If we just say the x is the element of a quotient group, this G by generated by G has the smallest possible order, then order of x nothing is equal to p. So this means we have to, in this way we have to prove that this result. Now we move to the another result that is saying that let G be a finite group and it is a normal subgroup of a G, and G is the element of a G, an element of a maximal order in G. So this G is the maximal order in G, and then we take a generator of a G intersection is equal to with this normal subgroup is equal to identity, and then we can say that if this opening, this is order of a Gn and order of a G are the same, Gn is the element of the maximal order in the quotient group of a G by n. Okay, so let first we note that x is the element of a G, has a order m, is a maximal order, then x n to the power m can be written x to the power m into n, and now this is nothing but is equal to n. So x order of x n divides by m, that is order of a coset x n is at most order of a x. So this means we can say that the order of the coset of a x n is at most the order of this element of a x. Now if G is the element of a G, has a maximal order n in G, so this means order of a Gn can be less than equal to order of a this G by above here. On the other hand, if we have to just assuming that order of a Gn is equal to suppose k, and n is equal to Gn to the power k, and this is nothing but G to the power k into n, and then k is the positive integer. This means G to the power k is the element of a, if these two are equal, then we can say that this is clearly G to the power k belongs to the n. So if G to the power k belongs to the n, and then we can say that G to the power k is equal to, you have a identity by the hypothesis. So that is order of a G must divides k, and so Gn this Gn is equal to order of a G by the above argument. So no element of a G by n has a order greater than the maximal order in G, and then conclusion follows by this thing. So complete the proof of this result. Now we have to another result which saying that let G be a finite abelian P group, and suppose G is the element of G has a maximal order, then G has an internal direct product of generator of a G and the sum subgroup of H. Okay, so proof by the lemma, this means order of a G is nothing but is equal to, if you go to this means if P group and order of a G is a prime power of a P. So by this result we can simply say that order of a G is equal to P to the power n for some n is the element of a Z star. If n is equal to 1, then G is cyclic of order P and must be generated by G, and assume now n should be greater than 1, and that G is not a cyclic. If it is G not cyclic, then by induction we have to induct this, assuming that lemma is held for all k where k is lies between 1 to n. Now, if G is the element of a G be a maximal order in G, then order of a G is equal to p to the power m for some n less m is less than equal to n. Now, we choose x does not belongs to the this G, where x has a smallest positive order. Suppose k is equal to generated by x, then by the lemma we can say that order of x is the nothing but is equal to k is the same as the order of x, and order of x is equal to p. So, this means the quotient group of this order of a g by order of a k, and order of a g is p to the power n, this is p to the power n minus 1. Thus, we can apply the induced hypothesis to g by k. Since k has a non-trivial subgroup and intersection of this is equal to, you have a identity. So, by the again this lemma j d to the power of k has elements of g by k of maximal order, and by the inductive hypothesis g by k is internal direct product of the generator of a gk and some subgroups k1 of g by k. Now, the third isomorphism theorem applies, then k1 is equal to, you have a h by k for some subgroup h of a k containing into h. So, we claim that this g is a internal direct product of a this generator of a g and h. So, let y is the element of a g, then y k can be written as a g k to the power some power t, and t is some positive integer b. Now, this can be written as g to the power t k b. Now, because b is the element of h, therefore, there exists some k1 k2 is the element of a k. Yk can be written in the form of a g to the power t k1 b, since k is a subset of h. So, y can be written as a g to the power k k1 b and some k inverse, and then this is nothing but equal to, this is the element of a h. So, this means this is generated by g. So, this is the element of a generated by g into h. This means g is nothing but is equal to, we can say that is the generator of a g into h. So, now we have to just say that remaining assuming the given that g is abelian. So, it is remain to prove that this is equal to identity. If we have a take a y is the element of a this thing, then yk is the element of a this intersection of this quotient group is equal to k. So, y is the element of a k and y is the element of a h, as k is a subset of h. So, by this implication y is the element of a h intersection k, and that is nothing but is equal to identity. So, we have this for g is a internal direct product of we prove the both the condition of a internal direct products of a group. So, we can say that this is clearly G is the internal direct product of the generator of a G and any subgroup of a H in this form. So, by this we have to write a corollary. Let G be a finite abelian P group and G is the element of G has a maximal order, then G is isomorphic to generator of a G and some direct product of some subgroup of this form. Now, let G be a finite abelian group and G is the internal direct product of a P group, we can just say it into this form. So, this is a proof the lemma, and after this lemma we have to prove the main theorem. We are assuming that order of this is equal to p1 eta 1 p1 eta 2 with pi is a distinct prime. So, by the lemma 3.1 the set Gi is a subgroup of a G. We will show that G is an internal direct product of this Gi. So, G is the element of a G, then Lagrange's theorem order of a G is the same as a this order of element of a this is the same as into this form where eta I. So, we will now show that internal direct product of a Gi if G is the element of a G, then the Lagrange theorem is say that order of a G is the nothing but is equal to p zeta 1 p zeta 2 and zeta n, where zeta I lies between 0 to eta I for all I, and then let a element is the nothing but is equal to order of a G upon divides the pi to the bar zeta 1, where a I are relatively prime and there exists some b I such that in the form of a1 b1 a2 b1, and that is equal to identity. So, G can be written as a G to the power of this all this thing, and this all this thing can be written as a G to the power a1 b1 a to the b2 and so on in this form. If we write into this form for each I, that order of g to the power ai bi to the power p to the power zeta is g to the power bi order of a g, and that order, this is nothing but equal to identity. So this means we can say that this is g a to a b I is the element of a g I. For all I, it follows that g can be written in the form of a g1 g2 gn, and then next we have to assuming that this x is the element of a gi intersection of union of all the gi's. If x is the element of a gi, and order of x nothing but is equal to is pi to the power ki for some k is the element of z, but x just is a element of this union, then x is a, if it is the element of this union, then x is a product of element whose orders are not divisible by p. So this is not divisible by p. We can say that order of x is not divisible by pi, because gi's are all are abelian. So this means we can say that this k must be equal to 0. If k must be equal to 0, then you can see we can say that if k must be equal to 0, so we can say that clearly x is equal to, you have a identity. Now we are in so this complete the proof of the series of lemmas, and now we are in position to prove the fundamental theorem of finite abelian groups. So finally we have to all the groundwork done for proving the this fundamental theorem. So we have to this series of 7 lemmas, we have to prove that 3.1 to 3.7, and by using these lemmas we can directly prove that this fundamental theorem of finite algebra. It says that every finite abelian group is isomorphic to a direct product of a cyclic group of a prime power order. So this is the means every finite abelian group is isomorphic to a direct product of a cyclic groups of prime power order. So let G be a finite abelian group, then by the lemma 3.7 we say G is the internal direct product of a GI, which all P groups by the and these are all the P groups. Then the corollary say that inductively we get each of GIs is decomposed isomorphically into the direct product of a cyclic group, and this completes the proof of this. So by the series of this lecture lemmas, we can just say that we can easily prove this fundamental theorem of finite abelian groups. We say that every finite abelian group is isomorphic to the direct product of a cyclic groups of prime order. Okay, so now we have a can extend this theorem into this form. Every non-trivial finite abelian group G is isomorphic to a direct product of a cyclic group of a prime order, then Zp to the power eta 1 and so on, in this form where pi is are some not necessary distincts primes, and eta I are the positive integer, and moreover the prime powers of this are uniquely determined by this. Means we have a isomorphic direct product of cyclic group of a prime order. G is isomorphic to into this form, and then we can prime powers of this are uniquely determined by the G. Now you have to combine the 2.3, 3.4, and then we have to getting into this form. So this theorem where Gi is the internal direct product of a subgroup Hi, and this is isomorphic to H of I, and then use the result where we say that if G is a cyclic group of order and then G is isomorphic to Zn, and then we complete the proof of this theorem also. So now I just take a one or two examples, and then we have to conclude the this using the this above theorem. We find only abelian groups of order 36. Now you just said that up to isomorphism 360 can be written as a 2 to the power 3, 3 square, and 5, and there are the possibility of a isomorphism up to isomorphism of a this Z23, Z3 to the power 2 and Z5, and then again we have to factorize this possibility of a 3. We have a factor of 2 plus 1, and then we have a 1 plus 1 plus 1, and then for this we have a possibility are 2 and 1 plus 1. In this way we have to write all the possible subgroups are there. These are the total 6 possibilities are there, because we have a this from this we have a 3 possibilities. You have a 3 plus 1 and 1 plus 1 plus 1, and then from this is equal to 2, you have a 2 1 plus 1. So, you have a 5 and one possibility for 5 is equal to this. So, total is you have a there is a 6 groups isomorphism by the previous theorem, we can say that in this form. If you take a U32 is an abelian group, and the order of a U32 is equal to 532, 532 is equal to you have a 16. So, it must be isomorphic to one of the 16, 16 means you have a right a 16, also 8 into 2 is a 16, and then 2 to the power 3 into 2 like this, 2 to the power 4, and then you can write it as 2 to the power 4 also, and then similarly all other factors are there. So, 8 into 2, then you have it write it 4 into 4, and then you have to write as 4, 2 into 2, then you have to write is equal to 2, 2, 2, 2, 2, and all are 4, and then we have to write in this 5 way, we can write into this form. Now, to determine which 32 is isomorphic to, we examine the order of elements. First, we note that there is a no element of order 16 in U32. So, it cannot be isomorphic to clearly this 36. So, this is not a possible. Z16 is a isomorphic to U36. Next, we observe that the order of a 3 is equal to 8. This indicates that the presence of an element of a order 8. So, that means we have to just take a possibilities are Z4 cross Z4, Z4 cross Z4 3, and then we have all this. This contain an element of a order 8, and these are the 3 possibilities where containing the order 8. Therefore, U32 has an element of order 8, it must be isomorphic to Z8 into 2, that means Z8 into Z2. So, Z32 is isomorphic to this means. So, it contains an element of order 8, then Z2 has an element of order 8, 32, it is must be isomorphic to we can say that Z8 and Z2, and then this can be written in the form on the form. So, Z8 into Z2 is the U32 is isomorphic to this. Suppose one more example, and then I will conclude. Consider n is equal to 200, and then scale 2 to the power 3 into 5, then again this is possibilities are there, and now there are the 3 into 2 non-isomorphic abelian groups of order 200, and then z to the power they are possible to this form, this and this form, this form. Okay, this means we have the possibility of a 2 to the power 3 is at 5 to the power 4 isomorphic to this 2 to the power 3, and then all this form is we have to writing in this form. And then one more I just take a as a result our classification we can prove a special case of a famous result due to Cauchy. Then Cauchy theorem for abelian group says let G be a finite abelian group, and suppose P is a prime power dividing order for G, then G has an element of order P. So, assuming that if G is divisible by a prime power, then G is not a trivial group. Let G be a let G as in theorem our this, so that means order of a G can be written in the form of a prime of this power of a prime, so where P divides order of a G, then P must be equal to Pi sum I, and then we say G has a subgroup isomorphic to Z of P eta I for some eta I greater than 0. However, in Z eta I the elements are P to the power eta I minus 1 has order P, and that means this complete the proof of G has an element of a order P is complete the proof of this theorem. So, by the application of this finitely fundamental theorem of a structure theorem for finite abelian group, and then we have a this fundamental theorem of finite abelian group. So, by this application we can easily prove the proof of this Cauchy theorem. We have already proved into the we have to this finite abelian group case, and then Cauchy theorem for non-abelian cases we have left. So, now I just stop this lecture here. So, we in this lecture we have to discuss the prove the fundamental theorem of finite abelian group and the structure theorem of finite abelian group, which will be help us to find the how many groups are isomorphic. If a group can be written in the form of a direct product is a prime powers, and then we can easily identify the number of possible way how to isomorphism of a group in this form. I think I have to stop today this last lecture of this series of 60 lectures here. I hope you understand very clearly what are the things I have to teaching for this over this series of 60 lectures. I cover all the course according to the syllabi of a University Grant Commission. I thank you for all of you, and I hope you have to understand the subjects. And if you have a comments and your suggestions are welcomed for improving me for this. So it's a very nice and new experience for using this media, this form of online lectures. So this means this all from my end. You have enjoying this, and I also enjoying this. I welcome all of the your thoughts, comings, and what the things is positive and negative things for improving myself. So I just say good luck you, and thank you very much for this thing. Thank you.